learners, very good morning to all. I'm Dr. Shagufta Khan from the School of Electrical, Electronics and Communication Engineering. So today in this lecture we will discuss about the types of HVDC system and an overview of that. And this topic comes under the subject facts and HVDC. So we can have three types of the HVDC link, that is monopolar link, bipolar link and homopolar link. So we will discuss one by one. So monopolar link. So here you can see the having one conductor negative polarity and the ground is used as a return path. So and this is the like you can see this one conductor we are using here as a negative polarity. This one is a negative polarity and the return path it is provided through this ground. Okay, so that is considering as a return conductor. Now we can operate either in positive or negative polarity, but usually prefer negative polarity in order to reduce the corona effect. So due to corona effect, so the major drawback in this system is power flow is interrupted due to either converter failure or DC link. So the ground return is objectionable only when buried metallic structures such as pipes are present and are subject to corrosion with DC current flow. So this is actually mainly we can have this option for the ground return, but it is restricted for some conditions. But this is the main advantage of the HVDC link. Here we are using only the one conductor, so the cost is also reduced. You can see. So that is the you see this. This is connected, transformer is connected, which is connecting to main this is a transformer which is connected to that AC system, and then we have the converter. So this converter will act as a AC to DC it is converting, so it is a rectifier. Then at the receiving end, this converter again from DC to AC it will convert, and then the transformer is connected to the other AC system, and this is the current which is I which is flowing here, and this is showing the thyristor based monopolar HVDC link. Bipolar link, you can see two poles we are using here. So one here two conductors are involved, one is operate at positive and the other it is operating in negative. So during fault is in one pole it will operate as a monopolar link. This is very popular, mostly we use that this bipolar HVDC link because we have that advantage. If any emergency condition, any faulted condition, we can operate it as a monopolar. This one, the return conductor we can have as a ground. So this is the possibility in case of the fault system also. We can operate bipolar in monopolar form of the link of the HVDC. Now the homopolar link, here two or more conductors with same polarity are used. Normally the negative polarity are used for both the conductors or more than two conductors due to the reduction of the corona losses. The ground is always used in this type of the HVDC link, and at the time of the fault we can operate this homopolar link as a monopolar link, so that time the ground can be used as a return conductor. Now see this again, this transformers we are having both the sides, so it is the rectifier end and this is representing the inverter end. Now the application of HVDC systems. So the main areas of application based on the economic and technical performance, we can have the long distance bulk power transmission, then underground and the submarine cables through by using that we can also have the HVDC transmission, and then asynchronous connection of AC system with different frequency, then control and stabilize the power system with power flow control, as we have the fast control of the power transmitted power in case of the HVDC system. So based on the interconnection, three types of the HVDC are possible, that is bulk power transmission, back-to-back connection and modulation of AC systems. Now, what are the purpose of that interconnection? Bulk power transmission, it is used to transmit the high power from one end to the other end. It is the best option of HVDC transmission, where bulk power is transmitted from one point to the other point, or from one area and to the other area, which are separated, which are far away from each other. Then the power flow control, back-to-back HVDC system, where the both the converters, rectifier inverter, both are placed at a one location. So that is also like to control that power flow. We can have that connection of the HVDC, that is called as a back-to-back HVDC system. Now to provide the stability to AC system, this is basically used to control the power and stabilize the system and connect two different frequency systems. And modulation of AC system is connected parallel with DC system. We can have both the transmission lines parallel, AC and DC link, where both AC and DC run parallelly, and it is mainly used to modulate the power of AC system in case of any fault condition. So HVDC is better option for above and cited purpose while compared with AC transmission system. Now this is the layout of the HVDC transmission. You can see here, this is the three-phase AC bus, or the AC interconnection is there. Then on this AC three-phase AC bus, we have some filters to reduce the harmonics here, and here the converters are connected in this bus. So that is it is showing the 12 pulse converter. These converters may be operated based on the thyristor control or based on the voltage source converter. So based on thyristor control, which we call it as a LCC based HVDC system, and based on the IGBT, we call it as a voltage source converter based HVDC system. So the converter operation based on the whatever the device we are selecting. Then there is a DC reactor, to smooth the power of the DC. Then we have the DC pulse. After the conversion from AC to DC by using these converters, we got this DC. So in this DC we can have that midpoint also. Okay, so that DC reactors are connected. Then it is the DC terminal, and DC surge capacitors are also there. Then DC line arresters, in similarly as we have in AC transmission. Then earth electrode is also connected. So after that, this is showing the rectifier station of the HVDC system. Similarly, we will have the inverter station of the HVDC transmission. Now the various parts of the HVDC transmission, we use converters at both the ends, like rectifier inverter, then converter transformer through which the converters are connected, then smoothing reactors, and then harmonic filters to reduce the harmonic at the AC side as well as at the DC side, then overhead lines, and then reactive power sources to basically improve the reactive power in the system. Then earth electrodes are also used. Converters, rectifier inverter, it is a main part of the HVDC system which has total control of the HVDC line. So usually consists of 2 or 3 phase converter bridge connected in series to form the 12 pulse converter. The total number of valves in such unit are 12. The valves can be packed as a single valve, double valve, or quadri valve arrangement we can have. Then earth valve is used to switch in a segment of AC voltage waveform, and this converter is fed converter transformer connected in star and delta arrangement. And the valves can be cooled by air, oil, water, or freon. So liquid cooling using deionized water is more efficient and results in reduction of station losses. So this is the configuration of the converters. So the converter unit, see this 3-phase AC bus, and it is connected to this transformer which are connected in star delta or delta star connection. Then we have the valve connection. So double valve, you can see this is the double valve or single valve arrangement we can have. Then quadrature valve or quadri valve arrangement, it is showing in the converter unit. The rating of the valve group are limited more by the permissible short circuit current and then the steady state load requirement. The design of valve is based on the modular concept where each module contains a limited number of series connected thyristor levels. So the valve firing signals are generated in the converter control at ground potential and are transmitted to each of the thyristor in the valve through a fiber optic light guided system. So the light signal received received at the thyristor level is converted to an electrical signal using gate driver amplifier with the pulse transformers. The valves are protected using snubber circuit protective wiring and gapless surge arrestor. This is actually rated with the LCC based HVDC converters. So this is only the operation which we are discussing here in case of the thyristor based HVDC systems. Now the converter transformer through which the converters are connected. 6 pulse converter, a conventional 3 phase or 3 single phase transformers is used. However, for 12 pulse configuration, we can have the 6 single phase 2 winding transformer, then 3 single phase 3 winding transformer through 3 phase 2 winding transformers. Then in converter transformer, it is not possible to use winding close to yoke since potential of its winding connection is determined by conductor valves. Now the smoothing reactors. So this is actually the reactors used to smooth the direct current output in the DC line, and there is a limits the rate of rise of the fault current in the case of DC line short circuit. And then normally partial or total air cooled magnetically shielded reactors we used in case of the HVDC system. So disc coil type windings are used and braced to withstand the short circuit current. To limit that current, we use this smoothing reactor. The saturation inductance should not be too low. Harmonic filters are used to reduce the harmonic at the AC side or the DC side of the HVDC link. So harmonics generated by the converters are of the order of NP plus minus 1 in AC side and up in the DC side, and NP in the DC side. So what is the formula to calculate the harmonics at the AC side and the DC side? So AC side we have that is NP plus minus 1, and the DC side that formula is N into P, where P is the number of pulses and N is the integer. So here P is total number of pulses. So which type of how many pulses we are using in that converter. So based on that we will calculate the harmonic, which harmonic is producing, that's AC side or the DC side. The filters are used to provide low impedance part to the ground for the harmonic current. They are connected to the converter terminal so that the harmonic should not enter to the AC systems. Okay. So however, it is not possible to protect all the harmonics from entering into the AC system, but magnitude of the some harmonics are high and filters are used to reduce that magnitude. So these filters are used to provide some reactive power compensation at the terminals. By providing the reactive power compensation, we can reduce the harmonics. Now the overhead lines. As we have the configuration that is monopolar transmission scheme is most economical, and the first consideration is to use ground as a return for the DC current. So but use of the ground as conductor is not permitted for longer use, and a bipolar arrangement is used with equal and opposite current in both the poles. So we have the option for the bipolar also in case of the long transmission lines, where we can use the ground as a return path. So in case of the failure in any poles, ground is used as a return path. Okay, so the basic principle of design of DC overhead lines is almost same as we have in AC transmission, such as configuration, towers and insulators. The number of insulator and clearance are determined based on DC voltage. The choice of the conductors depends mainly on corona and field effect consideration. So these effects we consider when we are determining the conductors. So as we know, in case of the LCC based HVDC system, we need the reactive power at both the converter ends, both the converters. So such converter does not consume reactive power, but due to high displacement of current drawn by the converter and the voltage in AC system, reactive power requirement at the converter station, that is 50 to 60% of the power transferred, which is supplied by the filter, capacitors and synchronous condensers. So that's why this filter, capacitor and synchronous condenser are used at the converter stations to maintain the reactive power. So synchronous condensers are not only supplying the reactive power but also provide AC voltage for natural commutation of the inverter. So due to the harmonic and transient, a special design machine is used to actually give the reactive power compensation. So this reactive power is required at both the ends of the converters for the operation of the HVDC converters. Then the earth electrode, resistively of an upper layer is higher, that is 400 ohm meter, and the electrode cannot be kept directly on the earth surface. So the electrode are buried into the earth where the resistivity is around 3 to 10 ohm meter to reduce transient over voltage during line faults and gives low electric potential and potential gradient at the surface of the earth. So that's why we use this earth electrode. The location of earth electrode is almost important because we have to see that effects of possible interference of DC current ripple to power lines, communication system of telephone and railway signals. So metallic corrosion of pipes, cable, sheet, etc. we have to include. Then public safety, for the public safety also we use this. Then the electrode must have low resistance less than 0.1 ohm and buried up to 500 meters into the earth. So these are the references which you can follow for this topic. Thank you so much. If you have any query, you can ask me.